Here is a problem. We have a nonlinear state space system. The state equation is x dot equals the quantity x minus 1 times u plus 2x squared minus 2u squared. The output equation is y equals 3xu. Both equations are nonlinear. The state equation has mixed xu terms, x squared and u squared. The output has an xu product. We are given 3 candidate set points and need to determine which ones are suitable for linearization. For a set point to be valid, the system must be in equilibrium, meaning x dot equals 0. Let us check each candidate. Candidate 1. X equals 1 and u equals 2. Substituting into x dot, the quantity 1 minus 1 times 2 plus 2 times 1 squared minus 2 times 2 squared. That is 0 plus 2 minus 8 equals negative 6. Not 0, so candidate 1 is not valid. Candidate 2. X equals 2 and u equals 4. Substituting, the quantity 2 minus 1 times 4 plus 2 times 4 minus 2 times 16. That is 4 plus 8 minus 32 equals negative 20. Not 0, not valid. Candidate 3. X equals 1 and u equals 1. Substituting, the quantity 1 minus 1 times 1 plus 2 times 1 minus 2 times 1. That is 0 plus 2 minus 2 equals 0. Perfect. Candidate 3 is our valid set point. Now we linearize at x set point equals 1, u set point equals 1. We need the Jacobian, the partial derivatives of f and g. The state function is f of x. U equals the quantity x minus 1 times u plus 2x squared minus 2u squared. The partial derivative of f with respect to x equals u plus 4x. At the set point, 1 plus 4 equals 5. The partial derivative of f with respect to u equals x minus 1 minus 4u. At the set point, 0 minus 4 equals negative 4. For the output function, g of x, u equals 3xu. The partial derivative of g with respect to x equals 3u. At the set point, 3. The partial derivative of g with respect to u equals 3x. At the set point, 3. Putting it all together, the linearized state space model is delta x dot equals 5 delta x minus 4 delta u. Delta y equals 3 delta x plus 3 delta u. In matrix notation, the A coefficient is 5, the B coefficient is negative 4, the C coefficient is 3, and the D coefficient is 3. Notice what these numbers tell us about the local behavior near the set point. A small perturbation in x amplifies x dot by a factor of 5, an unstable tendency. A small perturbation in u decreases x dot by 4, providing control authority. In the output, both state and input perturbations contribute equally with coefficient 3. This is the complete linearized model. Let us recap. We had a nonlinear system with x dot equals x minus 1 times u plus 2x squared minus 2u squared and y equals 3xu. In part A, we checked 3 candidate set points by plugging into x dot and requiring it to equal 0. Only candidate 3 with x equals 1 and u equals 1 satisfied the equilibrium condition. In part B, we computed the 4 partial derivatives of f and g, evaluated them at the set point, and wrote the linearized model. The result? Delta x dot equals 5 delta x minus 4 delta u, and delta y equals 3 delta x plus 3 delta u. 2 parts. Clean Jacobian linearization. Done.